Hello again. This is Math 2231 coming to you from the College of DuPage. And the title of this lecture is Squeeze Theorem Proof and Applications. And as always, please be an attentive learner while watching this video. I'm going to restate this squeeze theorem. I know we stated it in class already. So the squeeze theorem says if f of x is caught in between h of x and g of x for all x in some open interval containing c, except possibly at c itself, because we're going to be talking about the limit as x tends to c, which has nothing to do with what happens at c. And if, so this is a part of the if, and this is more if, and if the limit is x tends to c of h of x is L, and the limit is x tends to c of g of x is also L, then we can have two conclusions. There's an if-then in theorems, and so we talked about the if part. Then the limit as x tends to c of f of x does exist and must be equal to L. Now when you look at this picture, this does tell you that there is some interval between over here and over here perhaps, where f is caught between g on the top and h on the bottom, and they're both converging to a limit, even though they might not be defined as c. They're both converging to b, and this thing here is L. So you see you're squeezing f and forcing f to have the same limit. But we have to prove this, not just look at the pictures. So the proof is going to be an epsilon delta proof. So here we go with the proof. Now, by the if part, where we assume that the limit of, as x tends to c, of f of x and g of x are both equal to c, here's what we have for this is for h of x. So we take epsilon to be greater than 0, and we're going to have to find a delta such that we can use the epsilon delta definition. But for this epsilon greater than 0, I can find delta 1 such that whenever the absolute value of x minus c is between 0 and delta 1, that forces h of x minus L to be within that same epsilon. And there's a delta 2 that depends on epsilon perhaps, such that that will force, if I'm within delta 2, that will force the absolute value of g of x minus L to be less than epsilon. And then there's a third delta, because you see there is some open interval about c where this inequality is true. And so that means that there is a delta 3 such that this inequality holds whenever you're less than delta 3. So for this epsilon greater than 0, we're going to pick delta to be the smallest of those three. So that means all of those conditions hold. Then if 0 is less than the absolute value of x minus c is less than delta, that forces this to be true and this to be true. And by the triangle inequality, then, we know that this is true and this is true. So you see, since f was between h of x, but h of x is bigger than L minus epsilon, I can replace h by L minus epsilon there. And since g of x is less than L plus epsilon, I can replace the g of x with that. So we see that f is between those two, but that's the same thing as the definition that the absolute value of f of x minus L is less than epsilon. So you see, we've proven that there is an L, it's the same L, such that for epsilon greater than 0, we found a delta that would force this to be less than epsilon. This is a proof, and we are done with the proof of the squeeze theorem. Now, we're going to use the squeeze theorem specifically, and sometimes the squeeze theorem, depending on what textbook you're looking at, sometimes it's called the sandwich theorem, and sometimes people call it the pinching theorem. And you can think about, I sort of tried to justify calling it the squeeze theorem. A sandwich theorem, it's between two slices of bread. And pinching is, you could think about you're pinching it between your thumb and your index finger, perhaps. And so anyway, but we're calling it the squeeze theorem right now. But we're going to use the squeeze theorem to prove two very special trigonometric limits that we are going to be using as we go forward. So these are quite important. And so we have number 1 and number 2. I'm going to focus on proving number 1 first. It's the most complicated. And then I'm going to give you an algebraic proof of number 2. So here we go, and we're working to prove that the limit as x goes to 0 of sine x over x is equal to 1. And of course, x is in radians. Now, to avoid the confusion of two different x's flying about, statement of the theorem and other, we're going to do the proof of the first limit using a variable theta. Now, theta is an acute positive angle and measured in radians. And so without loss of generality, we're going to assume that theta is a small value of radians and that it is a positive number. You see it's small because we're taking the limit as theta in this case goes to 0, and so we only care what happens very close to 0. And the proof for it being negative follows very similarly to the proof for it being positive. So without loss of generality, sometimes abbreviated WLOG, we're going to assume this is true, and this is going to be our justification. Now we're going to start with a unit circle. So this circle that I have is the unit circle. Then we're going to be talking about triangles, circular sectors, and so forth. The small triangle is the one shown here. The circular sector is a circular sector, and then there's the big triangle. Now this is the unit circle, so that tells us that this point on the circle is 1, 0. So let's begin convincing ourselves that we do have these identifications. So look at the smaller circle, or not circle, look at the smaller triangle, this one. Well, if I say, what is the x coordinate here? This is a right triangle, and I go out this far to be x. But then I'm going to realize that the radius of the unit circle is 1. So if I take the value of the x coordinate of this divided by 1, that's going to be the cosine of theta. That tells us that the x coordinate of this point on the circle is cosine theta. Now similarly, here is the height that we have, and the radius is still 1. So the y coordinate here is the opposite over the hypotenuse, which is 1, and that's going to be the sine of theta. So you see, I have argued, I think effectively using right triangle trigonometry, that the coordinates of this point are cosine theta and sine theta. So that takes care of the smallest triangle. And let's talk about now the big triangle. So here's the big triangle. Again, this point is 1, 0. That means this side is 1. So I want to know, what is the y coordinate associated with this side? Well, y over 1 is the tangent of theta. Well, y over 1 is just y, so this is the tangent of theta. And this point is 1 because the radius is 1. So that point is 1 tangent of theta. And this is a sector arc, and we're going to talk about that. The other thing before we go on is the area of the tiny triangle is less than the area of the circular sector, which in turn is less than the area of the big triangle. And that should be geometrically obvious from this picture. Okay, so now I'm writing that. So the area of the big triangle is bigger than or equal to the area of the circular sector, which is bigger than the area of, and they're actually showing another triangle here, but the area of this triangle is going to be 1/2 the base times the height. So we're using that value that's shown dotted here, but we're using that, and that y coordinate was sine theta. Okay, so the area of a triangle is 1/2 the base times the height. So 1/2 of 1 times the height, tan theta, is the area of this triangle. Now the area of a circular sector is 1/2 theta r squared, but r is 1. And so this is 1/2 of theta because r is 1. And the tiny triangle is 1/2 the base times the height. The height we've already discussed is sine of theta. And so this is 1/2 sine of theta times 1. So this is what we have. Now what we can do is do some algebra. We're going to multiply each expression, all three of these. And again, we took theta to be a positive number, so sine theta is positive. So we're multiplying all the way through by 2 sine theta. Now, using the fact that the tangent of theta is sine theta over cosine theta, I'm going to get 1 over cosine theta is what this becomes. Here, when I multiply by 2 over sine theta, I get sine theta over, I get theta over sine theta. And here, I'm just multiplying by the reciprocal, so I get that this is bigger than or equal to 1. Now, the limit that we were studying really was sine theta over theta, so I'm going to have to find the reciprocal of all these. But whenever you have inequalities pointing, in this case, to the right, if I take the reciprocals, the inequalities are going to be pointing to the left. So the reciprocal of this is going to be cosine of theta. The reciprocal of this is going to be sine theta over theta. And the reciprocal of 1 is in fact 1, but notice that instead of them pointing off to the right, now the inequalities are pointing to the left. And again, all these are positive numbers. And here's some discussion about the without loss of generality. But now you see we've got the squeeze theorem going on, because this thing is in between the cosine theta and 1. So the limit of this thing, the cosine theta, as theta goes to 0 is, you can just plug it in, is cosine of 0, which is 1. So this side becomes 1. This side, the limit of 1 as theta goes to 0 is just 1. And so I got that this is between 1 and 1. So the squeeze theorem tells us that the limit as theta goes to 0 of sine theta over theta is equal to 1. Kind of cool, huh? I'm going to prove the second thing, and this is the statement of the second part of the theorem, and that is that the limit as theta goes to 0 of 1 minus cosine theta over theta is equal to 0. Well, again, without loss of generality, we can assume that theta is small and positive. So this limit we're trying to compute, theta goes to 0 of 1 minus cosine theta over theta is, and I'm again going to use a technique of multiplying all the way through by 1. That doesn't change the value. In this case, though, I'm going to be using 1 plus cosine theta over 1 plus cosine theta. Sometimes students say, how did you know to do that? Well, I'm pretty good at math, but also multiplying by 1 is there, and also this is tradecraft, because I know that there's some trig identities lurking here. So anyway, I multiply by 1, which is 1 plus cosine theta over 1 plus cosine theta, which is 1. So that means I can multiply this expression, 1 minus cosine theta, times 1 plus cosine theta. I get 1 minus cosine squared theta. And down here I'm taking theta times 1 plus cosine theta. So this is the limit as theta goes to 0 of the product. But 1 minus cosine squared theta is known to be sine squared theta. And I'm leaving the denominator the way it is. But now I'm going to use the fact that this is the limit of a product. So this is the product of the limits. So I'm taking one of these sine thetas over theta and putting it here. But then what's left is sine theta over 1 plus cosine theta. But the limit of the product is the product of the limits. So this is a limit as theta goes to 0 of sine theta over theta. Now I would be in trouble with this if I didn't have the first part of the theorem, because the first part of the theorem tells me that the limit as theta goes to 0 sine theta over theta is 1. I can't just plug it in because I would have 0 over 0, but I have the first part of the theorem, so I know this is going to be 1. And here, I can just plug it in, because when I plug in 0 in the denominator, I get 2. But when I plug 0 into the top, I get 0. So these two limits are going to be, the product of these are going to be 1 times 0, and this is 0, and so the proof is finished. And now we have these two important trigonometric identities that you want to commit to memory. Now let's apply these to some things, and we're going to use them later when we take the derivatives of the sines and cosines. Okay, so in this example, we want to find the limit as x goes to 0 of tangent of x over x. Now the first thing you try is just plugging it in, but you say, oh, I get 0 over 0, so that doesn't work. Well, but the tangent is the sine over the cosine, and so the limit as x goes to 0 of the tangent x over x is the same as the limit as x goes to 0. Here I'm putting the sine x over the cosine x, but there's the x, but I'm breaking it up this way. And now I'm going to use the fact that the limit of the product is the product of the limits, but we know that the limit as x goes to 0 of sine x over x is 1. And here I can do a just plug it in. If I plug in 0, cosine of 0 is known to be 1. This is 1 times 1 is 1. So the answer to this problem is this limit is. And if you were to draw a graph, you'd see, oh yes, that certainly is true. Although this graph is a little bit flaky, it was done with a computer, because you can see that there really is a hole there. This is not defined when x is equal to 0, but we don't care because this was a limit calculation. Let's look at another example. And so we're now trying to find the limit as x goes to 0 of sine of 4x over x. Now, and it talks here a little bit about when I say sine of 4x, that means that the sine parentheses 4x. So it's the sine of 4x. 4x is the argument of the function. Okay, so anyway, what happens here is we are going to multiply by 1 in a clever way. Actually, we're doing two steps here. So the limit as x goes to 0 of sine 4x over x is the same thing. I'm going to multiply by 1. So I'm going to multiply by 4 over 4. So 4 in the denominator and 4 in the numerator. But then the 4 in the numerator I am going to pull out of the limit sign using one of my properties of limits. So this is 4 times the limit as x goes to 0 of sine 4x over now 4x. It's important that these arguments match for our limit to be true, and I'm going to have to use a little bit of a change of variable. So I'm going to let y equal 4x. So now I have, this is the same thing as 4 times the limit of as y goes to 0. And by the way, if x goes to 0, then 4x goes to 0. So we're all good with that. So this is 4 times the limit as y goes to 0 of sine y over y. But we know this is 1. So 4 times 1 is 4. And you can see that geometrically, you see that that's what would happen as well. So again, we've used those limits to compute more complicated limits. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself, because self-care is important, and of each other, because we're all in this together. God bless you all.